Welcome to this tutorial on reinforced algorithm, a foundational method in policy gradient reinforcement learning. It allows us to optimize policy directly by sampling full trajectory and updating the policy based on return, making it a powerful tool. If that was heavy, just stick around because things will become more clear as we go further in the slides. So today we'll be looking at what is a policy, what is the objective function for reinforce, derivation of the policy gradient theorem, Monte Carlo sampling, and so on. Some some pseudocode and the final code. So let's look at this theorem. This wouldn't be a complete explanation, but let's look at the formal statement. So for a policy pi with parameters theta, the gradient of the expected return j of theta with respect to theta is, which this big term here where tau represents a trajectory sampled from the policy, and AT and ST are the action and state at time step t. RT is the return, and we'll be looking at all these terms in more detail later. So this is our objective. This is the gradient of the objective, and our objective is the expected return. So we'll look at that as well. So first, let's look at what is a policy. So policy is just a function that maps states to actions. So for example, if I'm in a game of chess, the positions of the chess pieces could be the states, and I will have all the different moves, and I would like to assign probability to each of them. So those will be determined by the policy pi. So our policy is represented by a neural network with parameters theta. So it's just a neural network. If let's say, for example, our is a vector of four dimensional vector, it would be an input to the neural network. And let's say we want to output two action probabilities. So in the final layer of the neural network, there would be two neurons, which would just throw out the probabilities. So if we have different values of theta, we have different policies. So it could be also thought of as the search for an optimal policy in the parameter space theta. Like that's just extra thing. We can ignore that. Our goal is to find the thetas that give us the best policy through the gradient ascent. And the best policy is the one that maximizes our expected returns. So we need something to optimize for which is an objective function, which is just the expected return of our policy pi. Expected, so a return is the total reward, sum of reward at each time step you would get by playing the game, and expectation over that, over all policies of the return for the return. So I would want to maximize the average return I would get by following the policy pi. So we should see the derivation in a greater detail to make things more clear. So for a given trajectory tau, so tau is a trajectory of state action rewards, next state action rewards. So we play a game, and the game starts at S0, and based on our policy pi, we select an action A0, and determined by the dynamics of the environment is the reward and the next state, so R0 and S1. And now we have S1, so we try to select an action A1 based on the policy. And while we are doing this, we record the whole trajectory, which is S0, A0, R0, and this tuple here. And we want to get the return R of tau, which is the sum of the rewards. So at each time step, I would expect a reward from the environment, and the sum of all the rewards from time step t till the end of the episode is the return for that episode. for that trajectory for that trajectory or that episode, we can say that. So our objective is this expectation, and we want to find its gradient. So to be able to maximize to for nudging our theta values. So we take we want to have it in terms of theta. So this term here is not a function of theta. It like not clearly a function of theta. So we expand this and using the definition of expectation here. So that's the function times the PDF of it, uh, and integrating over that. Sorry. Then we bring this nabla operator inside the integral. We can do that because it's tau and this theta. And then we can see that this can also be taken out of the nabla operator. It is affected by the thetas, but in here it's just a value. It's just a function of the trajectory. It's like it's dependent on theta, but not directly for now. So it's fine. We can take this out as well. And the gradient, we want the gradient of this probability of tau given theta. But if we use an identity of this identity here, so like the gradient of a function is function times the gradient of log of the probability, log of the function. So we get this expression here, and this is also an expectation. So this expectation of this term here as a function of uh, this probabilities. So what we have effectively done is taken r of tau out of the gradient. So we don't have to worry about like these things. And this is a something that is a function of theta. So we can find its gradient. So now let's take a closer look at this term. This is the probability of like having a trajectory tau given thetas. The probability would be let's say I'm in state 0, at like let's say I'm in state st at time t, then I select an action at, which is a function. So that the probability of that would be pi, given by this term here, pi of theta given st and at, and I end up in the next state st. So what the probability of that is determined by the environment. So it's not in our hands, but it would be given by the probability. This is known as the transition probability, which is a function of environment. And then we multiply like for all the states to like what would be probability of, like it's an and kind of operation. It's all chained together. So in those cases, we do multiplication. And then we take log on both sides. Uh, and the term on the left is in fact a function of environment and not a function of theta. So this becomes 0, and we are left with this other term, which is the gradient of sum of log probabilities. Here there should be an log. So, and I just have got a screenshot from somewhere, and that this, if we replace this term back in our original expression, we get to this point here. Only thing real in our in our expression here is this only thing that is taken from the environment, which is like the real world, is this rewards the return term, and we would like a way to use it in our updates. So one way of doing it is to go through the whole episode and calculate the return for each time step, and just after the episode finishes, we perform an update step by calculating the objective by this formula. So we just have the return for this episode at each time step. So we can calculate the returns for each time step and multiply it with the probability. And that gives us an expectation by summing over it. And we perform the update step. So we don't have to, we have a way of performing an update after each episode ends. So I play one game and then I do a learning step. So this type of methods are known as Monte Carlo. So where we sample a full episode, full experience, and then perform an update. So there is no requirement of estimates here. All these values are taken directly from the environment. Let's look at the pseudocode. So we need a policy pi, which is just a neural network, and we need a learning rate kind of thing, which is step size alpha. This we have to initialize the policy parameters theta, which is the initial values of our neural network weights. Then we have a infinite loop here in the pseudocode, but in practical case we would have like 100 or 1000 epochs, which is the number of episodes that we are going to play. And we generate a trajectory for the episode following the policy pi. And for each time step, then for each time step, we calculate the return g, multiply those g's for particular time t with the log probability of the action selected that time step, given the state, which is this term here, and then we perform one step of the gradient ascent. And that's the whole reinforce algorithm.